Welcome to the 26th lecture of graph theory. In the last class, we were discussing about perfect graphs, and we did a proof of Lavash of weak perfect graph theorem, which states that if G is a perfect graph, then its complement is also a perfect graph. This was the theorem. If G is perfect, then its complement is also perfect. Complement is also perfect. Now, the theorem is obvious from strong perfect graph theorem, which was proved much later, but then again we decided to do a proof of weak perfect graph theorem because it gives a good idea about the perfect graphs and good insights. So, in this class we will consider another proof of weak perfect graph theorem by Gasparian, which uses some linear algebra in its in the proof. In order to, in fact, instead of proving directly the statement that if G is perfect, then its complement is also perfect. So, what we are going to do is to prove a different statement, which was also proved by Lavash earlier. So, namely a graph is perfect. So, this is the statement: a graph is perfect if and only if for every induced subgraph h of G, the cardinality of h is less than or equal to omega into alpha. If you multiply the clique number and the independence number of any induced subgraph, then it should be greater than the cardinality of the number of vertices in the induced subgraph we are considering. If it happens for any induced subgraph, it is a perfect graph, and for a perfect graph it will happen. So, it is an if and only if statement. So, one thing is, see, why are we proving this? In order to prove the weak perfect graph theorem, which states that if G is perfect, then G complement is also perfect. Because it is obvious that if this theorem is true, that means any graph which satisfies the condition that every induced subgraph H satisfies the inequality, the cardinality number of vertices in H is less than or equal to alpha and omega, should satisfy that statement also, that if G is perfect, then G complement is also perfect. It says because this statement is symmetric with respect to the complement and the graph, because any induced subgraph if you take in the complement, the corresponding induced subgraph will again have the same number of vertices, that will be less than this product, because this omega will become alpha of H bar and this will become omega of H bar, right, because in the complement the independence number of the original will become the clique number, and the clique number of the original will become the independence number. So, this product is not going to change, just that the meaning of this alpha and omega changes, right. The numbers remain same, the product remains same, and this left side also LHS also remains same. Therefore, the inequality will be true for every induced subgraph for the complement also. So, therefore, the complement will be perfect, because any graph which satisfies this inequality for every induced subgraph is perfect. So, the complement is also perfect. So, it is enough to show that this inequality characterizes the perfect graphs. It is an if and only if statement for the perfect graph. Then we have already proved the weak perfect graph theorem. Therefore, we will try to prove this statement. See, one side of this statement is very easy. That means, if it is a perfect graph, then for every induced subgraph this inequality should be true, because you take an induced subgraph H. So, and its cardinality has to be less than or equal to its omega into its clique number, sorry, alpha into omega of it, because because it is a perfect graph. This induced subgraph is also a perfect graph, and then the chromatic number of this H is equal to the clique number. That means, we have a coloring of H using omega colors. So, in each color class is an independent set. So, it can contain only at most omega of H vertices, because omega of H is the biggest cardinality of an independent set in alpha of H is the biggest cardinality of an independent set in H. So, alpha of H is the maximum possible number of vertices in any color class, and we can cover all the vertices of H using omega colors. So, omega into alpha will be an upper bound for the cardinality of H. It is very straightforward for a perfect graph. So, the more non-trivial, the actual non-trivial part is to show the other way. That means, if a graph satisfies this inequality for all of its induced subgraph, then it has to be perfect. How will we prove this thing, right? So, the first observation is to see that, suppose you had taken an independent set, suppose G is the given graph satisfying that property, and you identified any independent set U in it, U of G, right. So, if you take the independent set U of G and remove U from G, so let us say G minus U is the graph which we get. What can I tell about the chromatic number of G minus U? What can you tell about the chromatic number of G minus U? You have just removed an independent set. G is a perfect graph. So, G minus U is also a perfect graph, because you have just removed some vertices from that. Any induced subgraph of G is going to be a perfect graph also. So, chi of G minus U has to be equal to omega of G minus U. Now, can we tell anything more than this? Can we tell what is the actual value of this thing? So, with some thought we can see that it has to be omega. So, is it trivial? See, because see, you started from G, you removed some vertices from. So, the clique number can only reduce, it can remain same, but we are saying that it has not reduced. Suppose it has reduced, suppose it has become omega minus 1 or less, right. Suppose omega of G became, sorry, omega of H became, so if G minus U is H, omega minus 1 or less, then what will happen? Then we can put back U to the graph. U is an independent set, we need only one more color to color the entire graph. So, because if this omega of G was equal to G minus U was omega minus 1 or less, we have colored using omega minus 1 colors and one more color for U, then we will be able to color G with we will be able to color G with omega colors, right, because omega minus 1 was enough for G minus U. G minus U was can be colored using omega minus 1 or less colors. So, G can be colored with omega, because U is an independent set. Then all the vertices, so we can get the one new color, and then G is colored with omega colors. So, G becomes a perfect graph. See the assumption again, to repeat, we are trying to prove that if G satisfies the inequality omega and alpha, so for every induced subgraph H, the cardinality of H is less than or equal to omega of H into alpha of H, then we want to show that G is perfect. So, we will do it by induction. For small graphs it is true, for one node graph, two node graph, it is very easy to check. So, we are assuming that all the smaller graphs, I mean all graphs with smaller number of vertices, it is true. So, when we took an independent set and removed from G, G minus u will definitely satisfy this inequality for all the subgraphs. So, by induction G minus u was perfect. That is why we could say that chromatic number and clique number for G minus u is same. Not only that, this clique number and chromatic number of G minus u has to be equal to omega itself, the original clique number of G, irrespective of which independent set we remove. The reason is that suppose it reduced, then we could have used one more color to color u, because u is an independent set, and then G is colored with omega colors and the clique number of G is omega, and then what so G is also perfect then, because every induced subgraph of G is perfect by induction assumption, and then G is perfect now like this. So, therefore, we can we know that we cannot do that. Coloring chromatic number of G has to be greater than omega, then only there is anything to prove, otherwise it is already proved. So, we can say that G minus u for any independence, whichever independent set you try, G minus u requires omega colors to color. That is why so probably G may require more colors, right, but we have to come up with a contradiction from that. So, if G minus u requires any colors, interestingly this is u can be anything, it can be one vertex, it can be the biggest independent set size itself, whatever it is, G minus u requires omega colors, right, to color. Now, what you do is you select a maximum independent set, some alpha, right, say let us say S is a maximum independent set, the cardinality of S is equal to alpha. Now, let us say S equal to, right, u1, u2, u alpha. This is the set of elements in S. Now, what we are going to do is to consider G minus S first. So, when you remove that independent set S, the remaining graph, as we mentioned already, can be colored using omega colors. The main thing is its chromatic number has not reduced, that is what we have sorry, its clique number has not reduced, it still has an omega size clique on, right. That means S, this independent set size cannot intersect with every clique in the graph, otherwise if it intersects with every clique in the graph, every maximum clique in the graph, the clique number would have reduced. So, that does not happen, that is why the clique number remains omega and the chromatic number is also equal to omega, because it is a perfect graph by induction hypothesis, smaller graph, right. Now, we see that. So, you consider an omega coloring of this right, you can consider an omega coloring of any so omega coloring of this G minus S, and then what will happen is so it has in fact omega colors, and the clique inside this G minus S, the omega size, any omega size clique inside G minus S has to have a representative color in it. But when we consider this coloring, we would rather do see like this. In fact, you take u1 and consider G minus u1, right, G minus u1. This can be, because u1 is an independent set by itself, you know the clique number will not reduce. So, the omega of G minus u1 is equal to omega only. So, the clique number will remain same. So, now because by induction hypothesis this G minus U1 also can be colored with omega colors. So, that consider that omega coloring, and this omega coloring correspond to omega color classes, right. We can call it see S11 S, or maybe we can just say it is A1 A2 A omega, these are the color classes. Now, we can say now we can say what will happen if I consider U2 from S and remove U2 from G minus U2. Again the same thing applies for G minus U2. So, the because its chromatic number is equal to its clique number because it is a perfect graph induction, and also it is equal to omega, as we have seen that its clique number cannot reduce by removing this thing, because if it reduces then you can get a new color and G also becomes perfect as we want. So, we can consider an omega coloring of G minus U2, and let us say omega, so A omega plus 1 to A omega 2 omega are the color classes, right. Now, for U3 also we can do the same thing, for instance, because chi of G minus U3 will be again equal to omega of G minus U3, and that will also be equal to omega, as we know. And then omega coloring of this G minus U3 if we consider, we can come up with another set of omega color classes. These are all independent sets, right. Each color class is an independent set, that will be A2 omega plus 1, A2 omega plus 2 until A3 omega, right. Like that, for when you remove Ui, you will get Ui omega, sorry, I minus 1 omega plus 1 to Ai omega, right. So, how many independent sets do you collect like this? Each color class, from what we are doing is you remove a vertex of S, because S is U1, U2, U3, U alpha. A vertex Ui is removed from the graph, and the remaining graph has a coloring using omega colors, not less, and we collect all the color classes, and these color classes are listed, say. So, maybe for it may be even more convenient to see these color classes as when U1 is removed, the color classes we got can be written as S11, S12, S13, maybe S, this is better probably S1 omega, and then when U2 is removed, the color classes obtained can be seen S21, S22, S23 and S2 omega, and then as when say U alpha is removed, you got U alpha minus right U alpha 1 comma U alpha, sorry, S alpha 2, S alpha omega, this many. So, how many sets are produced? Because here there are omega of them, another omega, total of alpha omega sets are produced, and add to this the original set S itself, because this itself was a independent set, this is S. So, this also is added. So, together this entire collection is alpha omega plus 1 independent sets, alpha omega plus 1 independent sets, right. And this alpha omega plus 1 independent sets are interestingly they have some interesting properties. So, namely, the most interesting property is if you take any clique of the graph. So, one thing is, for instance, if I had listed this alpha omega, this is S is the first independent set, second is S11 to S12 up to S1 omega, and then finally we will end up with S alpha 1, S alpha 2, S. So, corresponding to each of this independent set, we know that even if you remove S from that, there is a clique of cardinality omega in G, because the clique number cannot reduce by removing an independent set. Because if you remove an independent set and if the clique number reduces, then the remaining graph has a coloring with less number of colors than omega of the original. Then you can add give one more color to the independent set, and then we will get a omega coloring of G, which would make it perfect. Therefore, at least one clique corresponding to, I will say, Ks of cardinality omega remains in G minus S, in G minus S, in G minus S. Similarly, we will get a Ks11 in G minus S11 and so on. This is also an omega size clique. Similarly, here also. Ks alpha omega in G minus S alpha omega. Okay, this is what will happen. Now, not only that, if you take any of these cliques, for instance, you can take some clique here, we know that this clique does not intersect with this, because this outside in G minus S11, right, it is an omega clique in G minus S11. But then interestingly, that will intersect with all of the remaining things here, means the only independent set in which in this collection which it is not intersecting is exactly its partner here, right, to which it is paired. All others it will intersect. Why is it so? Because so for you can take any clique for that matter, and you can say that from this collection any clique of omega cardinality can intersect with only one of these things, and in particular have to intersect with all of these things except one. So, in particular we know which one for the cliques listed there, we know which one it is not intersecting from that, therefore, with all others it has to intersect. For instance, you can take a clique K. So, let us say the K is of cardinality omega. Now, there are two possibilities. K intersects with S, suppose our original independent set has no intersection with, that means K is in G minus S, that is K is in G minus S. Then we know that if you remove any ui from that graph, because ui belong to S, that will not affect this K, right. Yes, because anyway K was not intersecting Si, and we are removing vertices u1, u2, u3, u alpha were from S. So, when we removed the ui, that will not reduce K, that means that will leave K in the graph G minus u, right, that is a maximum clique in that. And the G minus ui graph after removing ui is colored with omega colors, and an omega clique should all the representative colors. So, that means it is part of all of S I1, S I2, S I omega, all the sets it is available. This is true for every I, therefore, it will be intersecting with all the color classes that we generate, right. So, that means all of this Sij kind of sets it will intersect, that is very clear. Now, on the other hand, suppose that clique was not intersecting with S, but if it is intersecting with S, there is the intersection can only be of cardinality 1, right, because this is 1. Why is it so? Because the K is a clique, and S is an independent set. It can intersect with only one vertex in S. Intersection can be exactly one, it cannot be 2 or more, because how can the clique intersect with more than one vertices in an independent set. Now, that is some uj, say this intersection correspond to some uj, right. Now, if we are not removing, so already S it is intersecting, and if it is intersecting with uj, then whenever any other ui is removed, this clique is not affected, it will remain in the graph, right, when you remove some ui other than in this uj, the particular vertex to which it is intersecting in S. So, whichever other vertex you remove from the graph, this clique will be intact, this will remain as such, and because we are coloring the remaining graph with omega colors, each color class has to have a representative from the clique has omega vertices in it, right, all of them has to get different colors. So, the clique has to intersect with each of those independent set, except some independent set in Sj1 to Sj omega, every other color classes of this form Si1 to Si omega S, so I not equal to j, will have an intersection with k, and among the sets Sj1 to Sj omega, only one independent set will be non-intersecting with k, because k, even after removing this uj, it will reduce to a clique of cardinality omega minus 1. So, it has to cut omega minus 1 color classes, except only one color class can escape intersecting with it. So, except one set, it has to intersect with all others. So, this is true for every clique. In fact, what we have told is, you take any clique of maximum cardinality in G, it can intersect with it has to intersect with all the sets, all the independent sets that we have created, that is S and Sij's, the total omega alpha plus 1 independent sets. From that, all of them it has to intersect except one. This, depending on the cases, we have analyzed that sometimes it can be S, or sometimes it can be some of the Sij's, but only one, exactly one independent set we can find to which it is not intersecting, and all the others in this collection it has to intersect. This is the key point, and in particular that this is true for any clique of cardinality omega. In particular, we have already seen that when you consider this each of the independent set in S Ij's, S and Sij's, total alpha omega plus 1 independent set, each of them has an associated clique which is in G minus Sij, or G minus that independent set. That means, there is a clique which does not intersect with. It is not just that every clique has to intersect with exactly one of them, it is also that there exists one clique which for each of them which does not intersect, and naturally if it does not intersect with this one, it will intersect with all others, because it has the possibility of not intersecting with only one set in this collection, right. With all others it has to intersect. It follows that so we have created a collection of independent sets, namely omega alpha plus 1 independent sets, namely S, S1 1 to S1 omega, S2 1 to S2 omega, and S finally S alpha 1 to S alpha omega. And corresponding to each of this thing, we have also associated a clique which does not intersect with it, and with among these sets, that is the only independent set with which it does not intersect, all others it will intersect. This is enough to prove our statement. What we are now going to make is to construct, we are going to construct a matrix where the rows are here, we will put it as 1 2 3 4 5, this column numbers are the vertex numbers, and these rows will correspond to the independent sets. This is S, this is S11, this is S12, and this is S alpha omega. The number of rows will be alpha omega plus 1, right, and this is an alpha omega plus 1 cross n matrix. Let us say this is A, and what will be here on the rows? In a row we will actually take the support vector of S here, means in a vertex belongs to S, then we will put 1 there, otherwise we will put a 0 there. So, whichever vertex belongs to S, we will put a 1 in the corresponding this thing, otherwise we will put a 0. Similarly here also, similarly here also. So, this is what we keep doing, right. So, we can put 1 or 0, namely whether this particular vertex corresponding in this column, in the corresponding to this column belongs to that independent set or not. Now, we will also create similarly a matrix which is an n by alpha omega plus 1 matrix, namely by this here the row numbers will be the vertex numbers 1, 2, 3, 4 up to n, and here this column numbers will be columns will correspond to the cliques k and k 1 1 k 2 1 2, like that we can say. The clique corresponding to Sij will be in the corresponding column, right, because if it is the row, this is tth row, the corresponding clique for this independent set will be put here, right, in the tth column. So, now when you multiply these two things, what will happen? So, you will definitely get a alpha omega plus 1 cross alpha omega plus 1 matrix. Now, what will be the entries of this matrix? So, some thought will reveal that, because what will happen, suppose if I take an ith row and ith column, if I multiply that corresponding an independent set and a corresponding clique is getting multiplied, right. This for instance they will not have any intersection, if no vertex is common to them. So, now if you think, you can see that whenever there is a 1 here, there will be a corresponding 0 here, whenever there is a 0 here, there will be a corresponding 1 here. Therefore, so not like that, whenever there is a 1 here, then it will be a 0 here, and whenever there is a 1 here, it will be a 0 here corresponding, because they do not intersect, right. So, when you multiply, you will get only zeros, is not it. Now, but on the other hand, if you take any other rows I and j, if it is I not I and j such that I not equal to j, then you say that it corresponds to different an independent set and a clique different from the clique associated to it, right, a different clique which was not its clique. Then what will happen? There is an intersection, they have to intersect, and if they have to intersect, and the intersection is only one, because a clique and independent set can intersect in only one place. So, we will, when you multiply, we will get exactly 1, right, because all other places it will be 0 into 1 or 1 into 0 or 0 into 0. In one place you will get 1 into 1. So, therefore, when you multiply, you will get 1. So, through the diagonal we will get 0, but all other places we will get 1, because ith row and ith column multiplies to 0. All other places we will get 1 1 1, and we know that such a matrix has rank. How much is the rank of that? Rank is full rank. So, therefore, the rank has to be alpha omega plus 1, right, because it is alpha omega plus 1 into alpha omega plus 1, and there, if you consider the columns of that matrix, they are clearly linearly independent, or rows of that matrix, they are clearly linearly independent. So, therefore, alpha omega plus 1 is the rank of that matrix. But in that case, you see, we multiplied A and B, and then when we got a matrix of rank alpha omega plus 1. That means, the rows of for instance, this A also should have rank alpha omega plus 1. That is it possible that the number of vertices in so the number of columns in A can be less than the number of columns in rows in A, because the number of rows here is alpha omega plus 1, the number of columns are n. So, if n was now less than equal to alpha omega plus 1, sorry, strictly less than alpha omega plus 1, that is n is less than equal to alpha omega, then what will happen is the rank of this matrix cannot be more than n, right, because there are only n columns less than equal to alpha omega. How can it have a rank of alpha omega plus 1? And if the rank of A is less than alpha omega plus 1, how can the product have rank alpha omega plus 1? So, but we know that by assumption this was correct, right, because H was less than equal to alpha omega for every induced subgraph, in particular for G also, right. So, this is clearly giving us a contradiction, because this A does not have rank alpha omega plus 1, and the product cannot have rank alpha omega plus 1, right. So, but then we see that here rank has to be alpha omega plus 1, this is a contradiction. Where is the contradiction coming from? The contradiction is coming from the assumption that G was not perfect. That is why we could select all those independent sets with that particular property, strange property, right, because if the G was not perfect, that is why we could assume that all, when you remove all the any independent set, the remaining graph is right, can be colored with omega colors, because the clique number does not reduce, and all those assumptions are based on the non-perfectness of G. So, that is what is going wrong here. So, G has to be perfect. So, we infer that G has to be perfect, right. It follows that if this particular property for every induced subgraph H less than equal to omega of H into alpha H is true, then G has to be perfect. Then of course, complement also will satisfy this property immediately, and then it is also perfect, that is all. So, because this statement H less than equal to alpha H into omega H is symmetric, because alpha and omega are just with when you go to the complement, they just the product remains same, alpha becomes omega, omega becomes alpha, and the cardinality of H does not change at all. So, that therefore, we have proved it in a different way. So, this is the proof of Gasparian, and in the rest of today's class, today's class and maybe tomorrow's, the next class also, I plan to cover a few special classes of graphs in the sense that so see why we are doing it, because we have seen several special classes of graphs already, which are all perfect, like chordal interval graphs, and then comparability graphs. Several classes we have already seen. It is a very important aspect of graph theory that we study special classes of graphs with structure, which comes from some applications, or so with much neater structure, so that things are much easier to see there in those classes, right, and also it gives insights about general statements, right. So, this is what we would like to do in this class. We will look at various special class of very well known special classes of classes in graph theory, and of course, we will not get into very a detailed look, we will not do a very detailed analysis of all these things. We would rather just casually look at these things, some properties and then some interesting facts, sometimes give a small proof. That is what we are planning, because this is only to make the students aware of such classes of graphs, and the interested students should read from other sources, right. The first class I would like to introduce is the class known as AT free graphs. AT free graphs. What is an AT free graph? See, the AT, which is called the asteroidal triple, it is called asteroidal triple, is a independent set of, in a graph G, suppose G is given. So, this is the graph. So, you can suppose you can identify 3 vertices. So, say x, y and z, such that there is a path between x and z which does not go through any of the neighbors of y, and also suppose there is a, and there should be a path between x and y which avoids the neighborhood of all neighborhood of z. That means no neighbor of z takes parts in this part. Similarly, there should be a path between z and y which avoids the neighborhood of x. Suppose you can identify 3 such vertices, independent set, that means mutually non-adjacent 3 vertices with this property, then we say that this is an AT, this is an AT. Now, a graph without an AT is called an AT free graph. If you cannot find an AT in a graph, it is called an AT free graph. So, you can get some examples of AT. For instance, you look at this graph, this small graph. So, can you identify an AT in this graph? This is so here if you consider these 3 vertices, it is an AT, because between these 2 we can find this path, it avoids the neighborhood of, this is the 2 neighbors of this, right. So, this thing, and also now between these 2 vertices, so for instance between these 2 vertices we can identify this path, this avoids the neighborhood of this this vertex, because this and this are the neighborhood of this, and between this and this we can identify this path which definitely avoids the neighborhood of this vertex, this and this are the neighbors of this vertex. So, this path does not contain any of its neighbors. So, this and this is an AT in this graph, and another AT, say for instance, suppose you look at this. Here for instance, this is x, y, z. Between x and y we can identify this path, see, and then see that avoids the neighborhood of z, because the neighbor of z is only this. Similarly, between x and z we can identify this path, it avoids the neighborhood of y, right, because the y's neighbor is here only. And now between y and z we can consider this path, and this path avoids the neighborhood of x. So, x, y and z is an AT, right. And so, another AT here you can identify, see, in a tree like structure also we can identify ATs here, because here see, here is a path, here is a path, here is a path. These paths avoids the neighborhood of the third vertices if you consider these 3 vertices. So, these are ATs. So, these are the kind of things ATs are, right. Now, a graph without an AT is called an AT free graph. So, there are several such classes of graphs where there are no ATs. So, one of the very interesting class of graphs which we have already seen without an AT is the interval graphs. Interval graphs are AT free. So, interval graphs are subclasses of AT free graphs. Why do we think that there are no ATs in that? So, for instance, in an interval graph, if there is an AT, we should be able to identify an independent set of cardinality 3. Let us say these 3 are the intervals corresponding to that, because see, any 3 vertices, they should have intervals in the interval representation, right. Now, what will happen, for instance, if I consider this vertex and this vertex, any path between them cannot avoid the neighborhood of this vertex. It is very intuitive, right. Therefore, so you cannot have an AT in an interval graph, it is very straightforward. And AT free graphs are a very large class of graphs. It also contains many other classes like the permutation graphs, which we will discuss in some detail in the next class, because they are also an interesting class. and another class is trapezoidal graphs. And a more general class which contains all these things, even interval graphs, right, are called co-comparability graphs. Co-comparability graph means the complements of comparability graphs. They are also these are all subsets of AT-free graphs. Right. So now, now there are some interesting properties of AT. So among AT-free graphs, among them probably the most interesting may be that AT-free graphs have always got a pair of dominating vertices, in the sense that you can find two vertices such that if you consider the shortest path between them, or a path between them, so they will be able to dominate all the vertices. So you remember what a dominating set was. It will become a dominating set. That means every other vertex will be associated to at least one of the vertices here. So the structure can be like this, right. So at least one of the vertices here. And moreover, one can tell, so there are connections inside this, there can be connections from here to here, but we can also say that no AT-free graph contains an induced 6 cycle or more, 6 cycle or a greater than equal to 6 cycle. Why is it so? Suppose you have an induced 6 cycle or bigger cycle, then you can find out an AT here very easily, right, because for instance this. So here is a path, here is a path, here is a path. This is an AT, right, because these paths between these two vertices avoid the neighborhood of this path between these two vertices avoid the neighborhood of this, and so on, right. So use this, and the fact that because again also this dominating pair can be, you can always say that you can select a dominating pair x y such that the shortest path between them is the diameter of the graph. So that is also known. So I don't prove all these things, I am just referring to a paper of Corneille et al. About the AT-free graphs. So that this kind of structural properties are described, which are very useful in studying the AT-free structure. We should try to prove, the student should try to prove that there is no edge from a vertex here to say a vertex to here, right. You cannot, the edges across cannot go too far away. See, one is because this is the shortest path between these two vertices, you have to make use of that. So we also try to make use of the fact that there is no induced 6 cycle here, right, induced 6 cycle here. So you can try to see how far an edge can go, and so essentially you can also go up to here. So it is given as an exercise, I leave it as an exercise, but here what interesting thing you can see is there is a certain kind of linear structure here. So the graph can be seen as expanding or progressing or growing starting from x towards y, or with some little bit of growth in the as it moves toward the side, but otherwise it is approximately linear. So this is a very vague statement. That is what you should read the paper of Corneille et al. About AT-free graphs. And again, our intention is not to describe lots of things about AT-free graphs alone. So we would like to also see some of the special classes. What is this subclasses of ATV graphs? What is a trapezoidal graph? What is a trapezoidal graph? So, you consider two lines, parallel lines. So, if you can associate with each vertex of the graph, a trapezoid can be like this, such that two endpoints of the trapezoids are so maybe I can draw like this. Two endpoints of the trapezoid are here, right? And say, so yeah, it can be right. So, see, these all each trapezoid correspond to a vertex, and whenever the trapezoids intersect, then there is an edge between them. If this is called a trapezoid model of the graph, if you can get a trapezoid model of a given graph, then it is a trapezoid graph. So, you can see that. See, the most important thing is you are not allowed to use arbitrary trapezoids. You have to make sure that it is 4 endpoints, 2 out of the 4 endpoints, 2 are on this upper line and then 2 are on the right line. See, it is very easy to see that if you do not allow arbitrary trapezoids, you just allow this kind of straight lines, then it corresponds to interval graphs, because this will become intervals now, right, though we are drawing rectangles. So, essentially they can be drawn in one line itself, interval graphs. So, it's I will leave it to the student to verify that these trapezoidal graphs are AT free graphs. It's very easy, just consider a independent set here, right. They won't be touching 3 non-intersecting trapezoids and try to argue that there cannot be any AT in it. You have to also try to prove that maybe the trapezoidal graphs are co-comparability graphs, right. So, like in sub cases when these interval graphs are considered, they are also co-comparability graphs. And the permutation graphs, which I will describe in much more detail in the next class, can also be seen as a special kind of trapezoidal graphs. What we do is you draw, so 1, 2, 3, 4. So, see this, so we can any trapezoid, suppose you only allow a line, for instance, this can be considered as a very special trapezoid, right. So, then it is called a permutation graph, the corresponding things. So, if it is a line, so you are just connecting a point here to a point here, 1, 2, 3, 4, 5, it will correspond to a permutation here. So, how that I will describe in the next class. And so, these are some of the special classes of ATV graphs. So, again we can see this as a class which generalizes interval graphs, because interval graphs probably are the most popular classes, both because its interest, its usefulness, and theoretically it is very interesting. And so, we have also seen that the chordal graphs are a generalization of interval graphs, because they do not have chordless 4 cycles. Interval graphs are also chordal graphs, right. And see, these are all perfect graphs, chordal graphs and all, but AT free graphs are not perfect. Why? Because they can have 5 cycles, induce 5 cycles in them, 5 halts are allowed, but of course 6 or more is not allowed, 6, 7 as we have seen. Why 5 cycles are allowed? So, AT free graphs need not be perfect, right. So, then okay, that is about AT free graphs. Another class of graphs I would like to introduce is again a generalization of interval graph, is the circular arc graphs, circular arc graphs. What is a circular arc graph? So, in interval graph we consider intervals on the real line. In a circular arc graph we consider arcs, in fact intervals or arcs on the circumference of a circle, right. So, it is clearly again the intersection graph of such arcs is called a circular graph. In other words, a graph is a circular graph if I can identify, if I can associate with each vertex an arc on the circumference of the circle in such a way that whenever 2 vertices are adjacent, the arcs intersect, otherwise they do not intersect. The same definition, the intersection graph of arcs on the circumference of a circle is called circular arc graphs. And why are they generalization of the interval graphs? Because if in this circular arc model, if there is a point which is not covered by any arc, you can break the circle there, and then it will turn out to be a interval graph, because you can draw it on the real line also then, right. So, therefore, it is a generalization of the circle, but when no point is unexposed, when exposed, that means every point has at least one arc going that, then it need not be an interval graph. Circular graphs can be very different from interval. Are they perfect graphs? Clearly they are not, because you can take any cycle and draw a circular arc representation for that. It is very easy to see that any cycle can be. So, therefore, but odd cycles are not perfect. So, the circular arc graphs need not be perfect, though they are to some extent they are similar, while but they are actually structurally very different. So, and like we define for interval graphs. So, if no interval is completely contained in another interval, then the corresponding model is a proper interval model, and if a interval graph has a proper interval model, then it is an interval proper interval graph. Similarly, we can define the proper circular arc graph, means if a graph has a circular arc graph model, so that no arc is completely contained inside another arc, then it is a proper circular arc graph model. So, similarly we can define unit circular arc graphs, where each arc has to be of same length. We can say unit length if you are considering or same length is better. So, because in an interval graph case it is same, right. So, but there are some differences between the unit interval graphs and proper interval graphs are same, but proper interval graphs and proper proper circular graph and unit circular graph need not be same. So, we do not have much time to spend on special graph classes so much, but interested readers should read it from Golombik's textbook Algorithmic Graph Theory or from papers. So, in the next class we will consider some other permutation graphs and some other intersection graph classes. Thank you.